A testing suite can report 100% coverage while the system remains unstable. As enterprise logic scales, the correlation between passing tests and reliability is dissolving. Enterprise applications have scaled into complex, adaptive systems, yet the methodology used to test them has remained static. Modern architectures run on dynamic variables. These systems rely on feature flags, asynchronous orchestration, and external cloud dependencies to maintain flexibility. This design makes the codebase inherently non-deterministic. Injecting the exact same input into a function will no longer guarantee the exact same output every time. Relying on static assertions in a non-deterministic environment creates a false sense of security. It allows specific architectural vulnerabilities to remain undetected until they trigger a production failure. On the left, a rigid box represents a static assert statement, needing an exact match. On the right, a fluid shape represents a dynamic microservice. If the dynamic response alters slightly, the rigid box immediately rejects it, even if the logic is correct. Development teams often fall into assertion hell, where the time spent updating expected test values exceeds the time spent on actual feature development. Non-deterministic flows, such as retry logic or AI-assisted decision nodes, cannot be accurately mapped to simple Boolean outcomes. This necessitates a shift toward validating the intent and correctness of the system's behavior, rather than focusing on exact output formatting. Building resilient software requires a testing layer that evaluates context, moving past the limitations of character string matching. To achieve contextual understanding, we need an architecture that programmatically verifies correctness while the application is active. This flowchart shows a standard ASP.NET Core 10 pipeline. To build semantic validation, we intercept the linear flow through this sequence. A semantic validator layer inserts itself immediately after the controller executes, routing data into a secondary loop before the final response is sent. This middleware captures the original input request and the resulting dynamic output response simultaneously. Instead of comparing that output to a static value, the middleware packages the request and response data alongside predefined business rules. Moving validation into the middleware allows you to evaluate live traffic against core business logic in real time. In this system, business rules are no longer written as C# assertions. They are defined as structured JSON configurations or prompt templates. The system combines the input, the dynamic response, and the business rule, sending them to a central AI validator. The AI evaluates the data. Does it satisfy business intent? It then outputs a JSON object with a pass-fail, confidence score, and technical reason. If a rule states that insurance claims under a specific amount are approved, the AI will pass a response like approved with standard processing because the meaning satisfies the rule. A single semantic rule can replace dozens of brittle assertion tests, as it is indifferent to variations in text formatting. This method decouples system verification from exact data formatting, allowing the underlying code to iterate without breaking the test suite. Beyond passive checks, we can now utilize an adversarial agent to actively challenge the system. Human engineers are limited by their own expectations. An AI model can systematically generate failure scenarios that a developer might not anticipate. We configure the agent by providing the raw API schema and the known constraints of the application. While human test cases remain linear, the agent generates chaotic inputs, partial payloads, delayed retries, and rapid concurrent requests. While a developer might test a negative claim amount, the AI agent tests a claim submitted twice within 3 milliseconds, using conflicting policy IDs. When the AI detects a vulnerability, it suggests a specific fix, such as adding a missing concurrency lock to the C# logic. Adversarial AI reveals the unknown unknowns, complex failure states that are difficult for human engineers to simulate manually. This linear flowchart represents standard pipeline. To be effective, AI validation must integrate directly into GitHub Actions or Azure DevOps. The pipeline inserts 2 new stages, semantic validation and adversarial testing, between traditional unit tests and the final deployment. This establishes a gatekeeper model. Deployment is blocked if validation fails, and flagged for review if the AI's confidence score drops below a set threshold. Running complex models on every commit introduces verification latency, which can slow deployment velocity. To manage speed and cost, teams can use small language models, or SLMs, locally for fast pre-commit checks. Full-scale cloud LLMs are reserved for complex flows during staging or nightly runs. Routing validation tasks between SLMs and LLMs balances architectural security with developer velocity. Delegating pipeline authority to generative models requires strict governance to manage the risk of incorrect model outputs. Critical decisions can use cross-model validation, where a test is routed through two distinct models. A comparator node then verifies that their results match before clearing the build. Maintaining comprehensive audit logs for every AI decision and ensuring manual override capabilities remain essential for critical infrastructure. This architecture changes the daily focus of both developers and QA engineers. Instead of maintaining test assertions, teams focus on defining validation intent and tuning AI rules. The shift towards semantic validation redefines the QA role as a strategist focused on system behavior. This transition begins by applying these principles to a single critical API today.
Before you head out, let me leave you with a small ask. If this video made your .NET brain spark even a little, hit that like button. It takes you 1 second.